Assalamualaikum warahmatullahi wabarakatuh. Hope everyone is in a good condition. Okay, we are in chapter 5 already. This is our last chapter, and this is our last lecture for this course before your test 2, which is scheduled next Friday. Okay, so in this lecture, for today's lecture, I will give you uh, information regarding what you need to know for your test 2. So I will give it randomly. So you need to watch all videos for this week's lecture so that you will not miss any tips for your test 2. Okay? Okay, without further delay, let's go to the first slide where for chapter 5, it is all about how to design our reactor and what do we need to consider in order for us to optimize the reactor design process. Okay, so almost all chemical engineering process contain three operations. Okay, what are the three operations? Okay, the first one is unit operation. Okay, where the first one is cleaning or pre-treatment. We know as cleaning or pre-treatment. This is the first one, and then the second one is the reactor itself. Okay, might be a furnace that need to be used, anything that we need the container or the apparatus or the mixing unit that we need to use in order for the reaction to occur. Okay, so number 2, chemical reactor. Then number 3 is unit operation, but this is separation. Previously we mentioned about cleaning or pre-treatment. For this one is separation. So basically, in any chemical process, we will have raw material and then the end product. Okay, so how to get clear picture regarding this, I have shared to you this link. Okay, um, let's look at the okay. Okay, I give example regarding steel manufacturing process. Okay, in this video, you will see from the raw material, I mean the starting point, and then the cleaning process, and then the furnace that is being used to melt the steel, and how to separate the molten steel and to produce it become a steel bar or a fine product. Okay, so I will keep on skipping fast forward the video because this video is quite long, about 6 minutes. You can watch it later. I have shared the link in post as well. Okay, so while watching this video, I will let you know which one is the cleaning process, which one is considered as the reactor part, which one is the separation part. Okay, let's watch the video. Okay, so okay, so this is the raw material. Okay, if you look at this is the raw material. Okay, raw material, and then okay, they need to use quite high a quite powerful magnet to clean the iron ore from any dust. So when the strong magnet or powerful magnet bring up the raw material or the steel, so all dust and all unwanted part will fall down. Okay, Okay, so this is the furnace. Okay, the furnace where you can see this is the furnace where the raw material will be put inside the furnace, and then it will be melted. Okay, the raw material will be melted to make it become molten steel like this. Okay, this is the molten steel, and then the molten steel will be transferred to another container. Okay, so this is the separation part where it is to produce the final product. Okay, so this is after we manage to produce the final product, where we call it as a part of separation process, because we need to separate the molten steel and convert it become a final product, and then it will be transferred to the conveyor, and then finally it will be inspected, and also will be sent to the customer. Okay, I think that's all. You can watch this video on your own. Okay, this is the example of what we have discussed just now. Okay, now um, reactor design basically means which type and size of reactor and method of operation we should employ for a given conversation. So we need to know what is the reaction, what is the process involved in order for us to design a reactor. I hope you can go to menti.com later on, because I will collect all your feedback and put in my teaching file. So you go to menti.com and key in this code. Okay, you can use this code 68431625, and please answer this question: what are the important parameters in designing a reactor? So anything that come into your mind, you can jot down, and then I hope I will have minimum 29 feedbacks, because uh, all of you need to give feedback, because we have 29 students for this course. And then I hope that I will get your initial thought regarding this question before we go further. Okay, this is an example of reactor design parameter, where the first one is the volume of reactor. Normally we will express it as V. Okay, and then flow rate F. Okay, flow rate, this is for CSTR, for PFR. Okay, because got flow, right? So, and then concentration of feed. Okay, concentration of feed. So, sometimes we use when we talk about feed, we need to have not so same goes to flow rate. If we talk about initial flow rate, we will label as FA naught. So if in any text, or in the test, if you find this term, that means this is a flow rate. And also, if you need to solve any calculation, you need to know this term. Whenever the question mention about uh, initial flow rate, or the feed entering the reactor is blah blah blah, so you need to use this FA naught. Okay, this is the first tip for your test 2. So in the question, you will not be I will not give you directly this term, but this is very important, because the value is being given in the question. But if you don't know that uh, that value is FA naught, later on you cannot solve the problem that is being asked to you. Okay, I hope you are aware with this. And then concentration of feed, reaction kinetic, normally we use negative RA, and then temperature and pressure. So these all are the important parameters in designing reactor. temperature. For example, if you want to do a crystallization of carbon dioxide, convert CO2 gas to solid CO2. So the temperature is very important. We need to control the temperature. Normally the temperature is 0 degrees C. Uh, and then it can goes up to 15 degrees C. Depends on the catalyst or promoter, okay, that we use. If we have promoter, might be we can use temperature up to 15 degrees C. If not, we need to use 0 degrees C. The same goes to the pressure. The pressure is, for pure CO2, we need to have pressure around 36 bar. But if we have a promoter, might be the pressure can go down to 32 bar. So we don't have to have high pressure to produce CO2 crystal, because pressure is equal to the amount of CO2 inside the reactor, which means if 36 bar, we will have more CO2 concentration as compared to 32 bar. Okay, so these all are important in designing reactor. So I give you example of a steel manufacturing process, CO2 crystallization. So that's why I previously I have mentioned that we need to know what kind of reaction uh, before we design a reactor. For plug flow versus CSTR, okay, for any particularity and for all positive ratio order, the volume of CSTR or mixed flow. CSTR is the other name of CSTR is mixed flow, okay. So you need to know, okay, mixed flow reactor is equal to CSTR. Will always be greater than plug flow. We have learned about this in week 11, where we have a asynchronous video 2, where you need to watch back that video, because one of the question is related to this part. So go back to that lecture, and you need to really understand that part. And then why we say that CSTR will always be greater than plug flow. Okay, we have discussed about that as well, so you need to go back to that video. And then area under the curve is very small for plug flow as compared to CSTR. Okay, this is the reason. Let me, I give you a clue. Okay, this is the clue. Okay, we have learned about this, and then we have learned that for PFR, it is area under the curve. Okay, let's say we have this conversion, 70% conversion. This is the conversion. This is FA naught over negative RA. So bear in mind, this is the graph that you need to plot. Okay, uh, this is will be the volume of reactor for PFR, but for CSTR is this. Why? Because PFR we have agreed that it is in the formula is integral form, but for CSTR it is in algebraic form. That's why we need to consider uh, this whole part. I mean square or the rectangle of that area. Okay, so this will be CSTR. That's why if you look at this part, PFR is smaller than CSTR, which is good, because we need to have, when we have a small reactor, that means we reduce the cost. Okay, we reduce the cost in designing or in manufacturing the reactor, and also we will not have to consider big space to install the reactor. In other words, if we have space limitation, we can install the reactor without any headache in our mind. Okay. Okay, this is the first video. I have uh, given to you several tips already. I hope you can uh, listen back if you miss it, and then get ready for your test 2. Okay, we will meet for the next asynchronous 2 video. Thank you.